Hi everyone, can you all hear me? If you guys can hear me, you can just type in a yes, and then I'll be able to get started with something. Okay, cool. So, so Sunday night, and a lot of you gathered to learn about graphs. You gathered to learn how to solve some interesting questions on graphs data structures on a Sunday night. So, I mean, it is enough to explain that you guys are self-motivated folks. So yeah, without wasting a lot of time, we'll quickly get started. But before that, there are a few announcements which I'll be making. So yeah, this session, you all know that graphs is a very core topic of data structures and algorithms, very famous in a lot of DSA interviews. I mean, you talk about FANG companies, good product based companies, good startups. When they interview, they if they have to check for good problem solving skills, or let's say uh, look into checking whether you can understand a network of data, or how to write recursive code, all sorts of stuffs, then they would throw a graphs puzzle at you, a graphs problem at you, right? So it's quite important to be comfortable in this topic. So what we'll be doing today is, even last week we had a session, but that session was not a DSA session. It was a kind of mix of development, high level design, and low level design. It was on designing a job scheduler from scratch. So how many of you were there in that session also? Can you just quickly type in a yes if you were able to attend our last weekend session on designing job scheduler? So those of you who were there in that, okay, few of you. So those of you who were there in that, like what we had done after this session was that we had asked everyone to share their key learning with us in some form, maybe a short summary of whatever you have learned from the session. And they did that by reposting LinkedIn post that we had created. So yeah, we have identified the person who was able to best summarize it, and he will be receiving his reward. The same thing we'll be doing today also. So when the session ends, I have Arshi with me here from my team. So she will be sharing a LinkedIn post of this session with you all. And you can just repost that and you can summarize your learning, whatever is your key learning from this session. And we'll pick the best summarizer and award him with a t-shirt and also with an access of our low-level design course. Because those of you who are keen to learn DSA, I'm sure that you might be finding something like low-level design to be a bottleneck in your interview processes, right? You might not have any ideas of it. So if you just want to skim through what it looks like and what really low-level design is, then then here's an opportunity for that. Okay, cool. So let's get started. So how many of you know graphs? How many of you have already heard about graphs or studied it somewhere, solved some questions on it? Can you just say yes? I'm just going to share my screen. It's a simple Google Doc which is empty right now. So if you can see my Google Doc, you can just type in a yes. Is it visible? Okay, so all of us have heard about graphs in one way or the other, right? So what is a graph? So how do you define it? So usually in computer science, it is said that graph is a collection of vertices and edges. So there are so many vertices and then there are so many edges. That's the idea behind this. Now, I also want to know how many of you know about graphs, knows the basics, but you're not comfortable solving questions on it. Or maybe the reverse way, like you sat in an interview and a question on graphs was asked and probably you couldn't solve it because of some reason. Okay, So, so once we have defined what graph is, what we can do is we can take some small steps, and then we will also touch base on some concepts. There are so many concepts, so it's not possible to touch base on all of them. But yeah, we'll pick some interesting ones and also do problem solving on those. That's how we are going to go. So, like if you have, let's say some nodes, let's say this is one node, okay, and then this is another node, and then this is another node. So you can have several nodes, right? And now let's say there are some edges. So let's say there is an edge from this node to this, right? And then there is another edge from here to here. And then let's say there is another one which connects this node to that, and then this node to that, and then another one, this node to that. Okay, now all these nodes are numbered. So let's say this is node 1, this is node 2, node 3, node 4. So you can see that there are 4 nodes over here, 4 vertices, and there are actually 1, 2, 3, and 4. Now, if you talk about edges, there are several edges. So there is an edge which connects 1 and 2. Now, when you talk about this edge, this is a bidirectional edge. So bidirectional means that I can go from 1 to 2, and I can also come back from 2 to 1. So it's not a one-way traffic, it's a two-way traffic basically. Okay, so if you talk about edges, the first edge is from 1 to 2, and it's a bidirectional one, as you can see. Then there is an edge from 1 to 3. So you can also express that. Okay. Similarly, there are lot many other edges. So basically, there are 4 vertices, and there are 1, 2, 3, 4, and 5. 5 edges are there, right? And in this case, all these edges are, bidirectional edges. But the edges can also have direction. So this is case of an, bidirectional graph, but you can also have a unidirectional graph in which the edges are directed. So if the edges are directed, that basically means that you can go from 1 to 2, but you cannot come back from 2 to 1, something like that. Okay, so let's say you just have this node, and then this one, and then the other one. Now let me pick this arrow. So let's say there is an edge like this, and then there is this edge, and then there is this edge. Okay, so you can see that this is the case of a directed graph. Now, how is a graph different from a tree, by the way? You guys must have learned about trees. Trees is also a collection of nodes and edges. Graph is also a collection of nodes and edges. So where does the difference lie according to you? So the difference, yeah, that's the most important point. So in case of tree, there are no cycles. Okay, but in case of graph, there can be cycles, and you can clearly see that there is a cycle here. Like you can go from 1 to 3, and then 3 to 2, and then back from 2 to 1. So this thing which I am demonstrating is a cycle. There are a lot many other cycles also. So 1 to 3, 3 to 4, 4 to 2, 2 to 1, and then 3 to 2, 2 to 4, 4 to 3. So there are several cycles, right? So in graph, there can be cycles. Do you see a cycle here in this graph? The directed one, does it contain cycles? No, it doesn't. If you think that this is a cycle, you probably need to think again. Because yeah, you can go from this node to this because you have a direction like that. And you can also go from here to here. But can you go from here to here? No, you can't. So this is not a cycle actually. So you have to be extra careful if the graph is directed. Okay, if the graph is undirected, then it is very easy to figure out whether there is cycle or not. But in this case, you have to look at the arrows and then only you will be able to pinpoint. Okay. Cool. Now, there are several representations of graph. I'll not be going into those theoretical details that what are the different representations and all, because those are boring stuffs, to be honest. Those are important ones. Why they are boring is because you can learn them on your own, or you can look at some of my lectures if you wish to. So I've talked about them in detail. Okay. So can you tell me like what are the different graph representations that you know about? So there is something called as adjacency matrix, and then there is something called as adjacency list. So what is adjacency list representation? You know, in adjacency list representation, what we do is for every node, we maintain a list. And what is that list? That list, I mean, for every node, you have a list of uh, directly connected nodes. As simple as that. For example, if you look at this graph, let's look at this undirected graph. If you're looking at one, then I would say, hey, you know, in the adjacency list of one, there will be node 2 and 3, because 2 and 3 are directly attached to 1, correct? Similarly, if you look at the adjacency list of 2, then here, you know, 2 is directly attached to 3 and 1, right? So we'll have 3 and 1. In the adjacency list of 3, can you tell me which all members will be there? Yeah, 2 is directly attached to 3, 1, and 4. You are right. So 4 should also be there. Good. In the adjacency list of 3, you can see 1, 2, and 4 are there. So I'll have 1, 2, 4. And similarly, in the adjacency list of 4, what will you have? So you can see 4 is directly attached to 2 and 3. Yeah, that's the thing. So this is an adjacency list representation, and this representation can easily be captured through a vector of vector, right? And you can call this vector of vector as some adjacency list, right? Because all of these are vectors. This is also vector, this is also a vector, this is also a vector. All of these are vectors. So you can have a vector of vectors. Now each vector inside it can have a different size. So like the size of this is 2, the size of this is 3. That's understandable because a node can be connected to variable number of children, right? Okay, now that we have understood this idea, we can easily construct a graph. I would say not construct, but we can easily, create an adjacency list representation of a graph if we have been given the, the edges. So let's say somebody says that, hey, you know, there is a graph. Okay, now my nodes, I am numbering them from 0. I'm not numbering them from 1. I'm numbering them from 0. So let's say somebody says that, hey, there is an edge from 0 to 1, and then there is an edge from 0 to 3. Then there is an edge from 1 to 2, and then there is an edge from 3 to 4. Okay, so let's say this is a scenario. Then what kind of graph it represents? So I would say that, hey, there will be a node with value 0 inside, and it is connected. Now let's say in this case, all my edges are undirected edges. So let's say this is connected to 1. Okay, and then you have another edge, 0 is connected to 3. So let's create a 3. Let's draw this connection from 0 to 3. And then you have 1 to 2. So let's draw another one, call it 2, get this edge. And then you have 3 to 4. So let there be another node with value 4, and 3 is connected to 4. Now this is the pictorial representation, but if you want to store its adjacency list representation, how do you go about it? So you would say that, hey, what I can do is I can first declare this vector, and now the number of nodes is 5. There are 5 nodes, 0, 1, 2, 3, and 4, right? So there are 5 nodes. So if let's say your nodes are numbered from 0 to n minus 1, in that case, you can say that it is sufficient to have an adjacency list of size n, right? And now I can say that the first member is a list of 0. So a list of 0 is basically a vector which contains the nodes which are directly attached to 0. So like here you can see 0 is directly attached to 1 and 3. So in this vector you will have 1 and 3. Cool. Similarly, in a list of 1, you will just be having the nodes which are directly attached to 1, right? So if you look at it, 1 is directly attached to 0 and 2. So that is what you will have here. And this is how it will keep moving on and on and on, right? Now, how to generate such a sort of vector? So how many of you know how to generate this vector of vector given such sort of input? Why I'm asking this question is because this is very basic thing. If you don't know this, you will not be able to relate to a lot of code that I'll be writing. So do you know how to create a vector of vector given a sequence of undirected edges? Okay. So it's super easy actually. See, can I say one thing, that if 0 is connected to 1, that means there is a connectivity from 0 to 1. And if the edges are undirected, so it means there is a connectivity from 1 to 0 also. So in the adjacency list of 0, 1 should be there. And in the adjacency list of 1, 0 should be there. And I can generalize it that if you have an edge from x to y, then it means that in the adjacency list of x, y should be there. And in the adjacency list of y, x should be there. As simple as that. Do you guys agree with it, whatever I have said? Yes or no? Everyone else? Yeah. So what we can do is, let's say these are the pairs and total number of pairs is m. Okay. So what we can do is we can write a for loop for I equals to 0, I smaller than m, I plus plus. Okay. And then we can take input. So we can do cn of x and y. And now super simple thing. We'll just say that, hey, in the adjacency list, which corresponds to x, I want to do a pushback of y. And quite similarly, in the adjacency list of y, I want to perform a pushback of x. This is exactly what I had told you. Okay, these two lines, what they are doing is that if there is an edge from 0 to 1, then in the adjacency list of 0, I want to push 1. That's what we are doing here. And then in the adjacency list of 1, we want to push 0. This thing, as you can see, right? Okay, so this way you can very easily create an adjacency list. And once you have an adjacency list, then you can do a lot of things with a graph. The simplest thing that you can do with a graph is traversal. Okay, simplest thing can be traversal. Instead of that, we can use a map. You can do that, but you don't need it if your graph nodes are labeled from 0 to n minus 1. Because in that case, you don't need a special kind of key. You know that the index of the vector itself can serve the purpose of the key. Okay. Hope that makes sense. Because with usage of map, there is some overhead involved in the computation of hash function and all sorts of things. Okay, so have you heard of any graph traversal? Anyone who ever wrote a code to perform graph traversal? What is the most famous graph traversal that you have heard of? Yeah, DFS and BFS. So let's pick DFS. Okay, let's talk about DFS. So it stands for depth first search, and it can be implemented both recursively as well as iteratively. But let's answer one very simple question at this point of time. Like, how is a graph traversal going to be different than tree traversal? So one of you has this question: is it similar to tree traversals? So how is a graph traversal different than tree traversal? Let's answer it. In case of tree, the remarkable thing is that there are no cycles. So let's say there is a node, it's a random node, okay? And then there is an edge coming out of it, the left child and the right child, okay? And then let's say there is another node here, yet another node here. And then again, there are a few more edges coming out of it. So the most important thing I want to remark here is that there are no cycles at all. Now, if there are no cycles at all, and let's say we wish to use simple idea of recursion to perform traversal, then we can say that, okay, once we are at this function, so let's say DFS of 0 can call DFS of 1, and then DFS of 1 can call DFS of 2. So this is how things can happen. But if there are cycles, things can go wrong. So how? Let's say DFS of 1 calls DFS of 2, DFS of 2 calls DFS of 3. Now DFS of 3 can again call DFS of 1. So your set of recursive calls might get trapped inside this infinite cycle, right? So this is one problem. So in case of graphs, what we have to do is we have to keep track of the fact that which nodes are visited and which nodes are not. Have you done something like this before? Have you guys ever implemented DFS traversal on your own? So yeah, you can use a hash map to store all those things, but not really needed because as I told you, these graph nodes are labeled from 0 to n minus 1. So why don't you use just an array flag? So let's say there is a Boolean vector. I'm calling it flag, or let's call it is visited. And this is of size n. If there are n nodes and initially everything is false, that means none of the nodes are visited so far. And now, what is the core idea going to be? The core idea is that before visiting a node, if let's say we are going to touch a node, we will mark it as visited. So let's say we want to start a journey from 0. So we would say that is visited of 0 is true. And having done this, I'll call DFS at 0. Now comes the most important thing, implementation of DFS. So if you have to implement DFS, let's say there is a void function, void DFS. Okay. So how should the implementation look like? What is the idea behind DFS? So what we can do is, if you are at a node, so let's say you are at node 1, what do? You look at your immediate neighbors and then you recursively call them. But you have to exercise a caution. And what is that caution? You have to check whether those nodes are already visited or not. Because think, if this node called this node and this node called this node, here you don't want to call 1 again. Why? Because 1 is already visited. So what you can do is, you are free to traverse on your adjacency list. So let's say you traverse on, you are current, so your adjacency list is a list of current. You're just traversing that vector. And now what you want to do is you want to check whether the jth member of your list is visited or not. So what I mean is, let's say adjacency list of 1 contains 0. So you want to check whether this 0 is already visited or not. So what you would do is, you would check if in this list, the jth member is not visited. So if not of is visited, this thing. Okay. Do you understand the meaning of this expression? So if the jth member of my current list is not visited, then what do I need to do? Then it means that, hey, I can traverse that node. But before I traverse that node, as I did here, I'll mark the is visited of that node as true. So I would say is visited of this little thing should be made true. And then we need to start our DFS journey right from that node. Okay. So that's the idea. Simple. And yeah, whenever you visit a node, the simplest thing that you can do is you can just print it, right? So this way you can perform traversal. So does it make sense? Does this code make sense that how it uses adjacency list and uses it to perform DFS traversal of a graph, right? So there are just two main things involved: the adjacency list, which is a vector of vector, and the second thing, which is visited flag, to keep track of the fact that which nodes are visited and which nodes are not, right? Okay, now let's make this question a little different. So now we know how to traverse a graph. if I ask you that, hey, can you just go ahead and check whether a graph contains cycle or not? Because so what I want to do is I want to check whether a graph contains cycles. Even if it has one cycle, you should return true. And if it has no cycle, then okay. Then okay, it doesn't have any cycle. So if you look at this graph, for example, this one, what should be the answer? True or false? False, because there are no cycles. And what should be the answer for this graph? It should be true because there is a cycle. In fact, there are many cycles. So how can you just introduce a small tweak, a small change in this code so that we are able to check whether there's a cycle or not? So the idea is super simple. What is the idea? Let's talk about this. So like whenever you are doing DFS, what happens? You start from a node and then you call another node if it is unvisited. Then you call another node if it is unvisited. Now let's say you are at 3. When you are at 3, what would you be doing? What is the first thing that you do at a node? You look into its adjacency list. The adjacency list of 3 contains 1 and 4. When you look for 1, you see that, hey, this 1 is already visited. If this 1 is already visited and there is still an edge from 3 to 1, then it definitely means that there is a cycle. Why? Because you started somewhere from a node, let's say 1, and now you are here. So there was some path that took you from here to here. And now if you see there is yet another edge connecting it, that means a cycle has been formed, right? So you came from 1 to 2 to 3 via this path, okay? And now you happen to see that, hey, there is yet another edge. So it is guaranteed that there would be a cycle. So what we can do is we can introduce a small check, and that check can be introduced here, that if if ever we see that a member of the adjacency list is already visited, that means definitely there is a cycle. Okay, does this intuition make some sense? Do you guys understand that how it can be useful in determining cycles? Right? So what we can do is we can just write an else condition. Now else condition, okay, first of all, does it make sense to everyone? Do you guys follow how using this idea we can assure whether there is a cycle or not? Okay. So if this condition is false, if that particular node is already visited, we can probably mark a variable as true, which is initially false. So let's say there is a global variable answer, which is false. We can make it true here. By the time this algorithm is over, we can just check the value of answer and then the job gets done. But if you probably look at it, there is some problem with this approach. There is one slight issue with it. Can somebody point that out? What is it? So let's take a very simple example, very, very, very fair example. Let's say this is the graph. Does it have cycle? No. Now let's say you call DFS at 0. So when you call DFS at 0, you first made is visited of 0 as true. Now when DFS of 0 is executing, what do? You traverse the adjacency list of 0. The adjacency list of 0, what does it contain? It contains 1, right? And you will check, is 1 visited? 1 is not visited. So what you will do is you will make a DFS call to 1. So from 0, you came to 1. Now just imagine when DFS of 1 is executing, in the adjacency list of 1, will you have 0? Of course, yes, because 1 is connected to 0. Now you will see that, hey, 0 is already visited. So you will come to this else condition and you will say that, hey, there is a cycle, which is not right. So what actually is happening is you are considering this edge as cycle. And intuitively, you can say that, yeah, in case of undirected edge, every edge is a cycle, because you can go back, you can go from 0 to 1 and come back from 1 to 0. But you know, intuitively I would say that, hey, this should not be regarded as a cycle. So this is an exception. The exception is that if there is a back edge to your parent, then do not consider that as your cycle. And how can that be ensured? That can simply be ensured by, passing the parent to the function call, right? So what we can do is that whichever function called the current function, that information we need to gather. So let's say when we call for DFS of 0, then there is no parent for 0. That is the first call. So we can pass the parent as -1. And the logic that we can write here is that there is something called as a parent. And now here in the else condition, we would want to have a check. And that check would be that if the node, which is this, if this node is not equals to parent, if it is not equals to parent, then only it means that there is a cycle. Because if it is same as the parent, then that's not the right thing to do. Currently, we are only talking about undirected graphs, okay? So if this is not equals to parent, then this is something that we do, okay? Now, because we have to pass parent to the DFS call every time, so can you tell me what should we pass here? So this thing happens to be a child of current. Yes. So what we should be passing over here is nothing but current. That's the idea. Okay. Anything that you feel missing with this code or something? I'm not going to run any code. I want you guys to, just pick these code towards the end, run them on your own. And if you feel anything missing here and there, you should be able to, fix that. But yeah, for now, we know how to determine the cycles. But now tell me one thing. Is this approach going to help us find the cycles in case of directed graph also? Let's say you have directed graph and you use the same approach. What will happen? So let's see what will happen in that case. Like when I look at this directed graph, does it have a cycle? The answer is no, it doesn't. Let's say this is 0, and this is 1, and this is 2. If you use this particular algorithm, in this case, what will happen? DFS of 0 will call DFS of 1. Okay. DFS of 1 will call DFS of 2. Right? This DFS of 2, when DFS of 2 is called, 2 is not connected to anything. 2 is not connected to any of the nodes. So, so basically the job is done. All right. So 2 will be popped. It will be removed. Now the control comes to DFS of 1 again, and then it goes back to DFS of 0 again. Now, if you take a look at it, see, when you were doing DFS calls, you moved from 0 to 1, and then you moved from 1 to 2. Now, when control comes back to 0, it tries visiting 2, but it sees that 2 is already visited. If 2 is already visited, is it sufficient to say that there must be a cycle? Had these edges been bidirectional, then it would have been right to say. Because you could say that, hey, I was able to traverse from 0 to 2 by some sequence of edges, and now I can see there is one more edge connecting 0 to 2. So there must be a cycle. But because these edges are directed, so this logic is not correct. So this logic is not correct. 0 is connected to 2, but there is no cycle present over here. So how do we distinguish that? How do we take care of situations like these? So here we'll say that, if you have such kind of directed graphs. So let's say this is a node, and here comes an edge which connects it to another node. And then here comes an edge which connects it to yet another node. At this point of time, let's say there is an edge which connects this node to that node, then it is guaranteed that there is a cycle. Like, can you see there is a cycle here? There is. But in this case, what is happening is that, let's say this is node 0, and this is node 1, and this is node 2. So if you look at the recursion call stack, DFS of 0 is lying inside the call stack, and then it made a call to DFS of 1. So DFS of 1 is lying on top of DFS of 0. And now DFS of 1 called DFS of 2. So DFS of 2 is lying on top of DFS of 1. Now when DFS of 2 is being catered to, you see that 2 has a connection to 0. 2 has a connection to 0, and 0 is already in the call stack. So if this is the case, that your current node is pointing to a node which is already in the call stack, then it is guaranteed that there will be a cycle in directed graph. But if that node is not in the current call stack, then cycle will not be there. How? Let us just see that. So if you just look at this situation, in this situation, can you think what would have happened? Like DFS of 0 called DFS of 1, and DFS of 1 called DFS of 2. So this same scenario would apply, right? But now when you look at DFS of 2, there are no outgoing edges from here, right? So there would be no further calls, and now DFS of 2 has exited. So this 2 would be popped, right? And now similarly, when you look at 1, DFS of 1 had only one edge, and it has traversed that, there is no other edge. So DFS of 1 will also be popped. Now when you come to DFS of 0, you see that there is another edge, and this edge is connecting us to 2, but that 2 is not in the call stack. Because that 2 is not in the call stack, so it is guaranteed that there is no cycle. Do you see the difference? So in case of directed graph, it is not enough to say that, hey, if there is a back edge to already visited node, there must be a cycle. No. If there is a back edge to a node which is in the call stack, then there will be a cycle. And it's very important to understand this difference. How many of you get this difference? Can you just type in yes or no if you understand it? Yeah. It requires some fair amount of understanding of recursion in order to appreciate this. Yeah, I think just I would say probably when we share recording with you, just look at that recording again. That should be helpful. I would like to move on to some questions from here. But the basic idea, just to sum it up, is if you understand the idea of call stack, recursive call stack, in scenario like this, you'd see that function of 0 would call function of 1, function of 1 would call function of 2, and now function of 2. Now do you see function of 0 has called 1, 1 has called 2, and now that 2 sees that there is a connection with 0, but 0 is in the call stack. So there is a back edge. So you know that connections, that directed connections, they somehow form the, yeah, you get the point? But if it was not in the call stack, then those directed edges will not form a cycle. That's the idea. So how do we implement it? We can implement it in a very, very simple manner. So what we can just do is we can simple DFS. Let's make this simple DFS. Now here. Yeah, so what we are doing here is that it's the same thing. We are checking whether the current node is visited or not. If the current node is not visited, we mark it as true, and then we visit it. In the else case, what we are going to do is we want to check whether that node is already in the call stack or not. So for that, guys, we can do a very simple thing. We can have another vector of Boolean. Yeah, you can call it is in stack, and it will be of the same size. Okay, and you can initialize it all to false. the same size n. Okay. Now what you can do is whenever DFS call for a node current is made, you can change this of current to true. Okay. And only when this entire for loop is executed, then you can turn this back to false. This is the idea that you can use. Now what it means that if a certain node is in the call stack, then this value will be true, correct? So what we are going to do is whenever we come to the else case, inside this else case, we will be interested in checking whether the current node is inside the call stack or not. Now, how we can do that? We can do that by looking up for this thing. We will say if this of that node is true. If this value is true, that means this particular node is already in the call stack. And if it is already in the call stack, then we need to say that, hey, there must be a cycle for sure. That's the idea. So you can see like how it works. Like whenever DFS is called for a particular node, we mark uh, this particular variable for that node as true. And we make it false again, but we do it only when that node is popped or from the call stack. If it is not yet popped from the call stack, the value of this thing for that node would still be true. And if at any point of time you end up seeing that there is a back edge to a certain node for which this variable is true, then that means we need to reset this answer to true. Why are we resetting it to false? Because if you do not reset it to false, you will be in trouble. You will not be able to identify whether this node has been removed from the call stack or not. When it is removed from the call stack, you need to, you get that case, right? I mean, you just look at this case, DFS of 0 called DFS of 1, it called DFS of 2. Now you want to reset that variable for 2 as false. If you do not set it to false, you will see that 0 has connection to something which is already in the call stack. So to differentiate that, you have that thing, okay? Cool, so now once you understand this idea, we can go on to solve a very interesting question. So I'm just going to share link to that question with you guys. So I'm just sharing it in the chat box. You guys can just open up this link. This question is also present on my screen, as you can see. So just read this question once. And after you have read the question, you can just let me know whether you would understand the problem statement or not. This question also happened to be one of the questions to be asked in a very famous company's interview. Not just once, a lot of times. So it's a good question, actually. Okay. Uh, so anyone who could understand what the problem statement is trying to say? Anyone? Okay, good. Okay, so now let us read the question. I'll help you understand it if you could not understand it on your own, because the very first step in uh, problem solving is that you understand your question quite clearly. I mean, do not put an ounce of thought until unless you are crystal clear with the problem statement. Okay. So the problem says that we have a string array recipes. So there are different recipes, like there are two recipes, bread and sandwich. Okay. And then for each recipe, there is a list of ingredients. So a bread, let's say bread requires yeast and flour to be made. So this is the ingredient. These are the ingredients for bread. For sandwich, these are the ingredients. So for sandwich, somebody says that I need bread and I need something else. I need meat. Okay. So these are the ingredients for sandwich. Now, if you look here, the important thing to understand is that apart from recipes and ingredients, okay, so first thing, for every recipe, you will have a list of ingredients associated with it. So if there are 100 recipes, that means you are going to have 100 lists of ingredients. Okay. So you can see that this thing, this ingredients, it is actually a list of list or vector of vector. Apart from that, there are supplies. So supplies are, raw materials. These are raw materials which are available to you in your kitchen. So you have a lot of yeast, flour, and all other sorts of raw materials. And now you can use these raw materials to construct a recipe. So if you see that, let's say bread, to make bread, I need yeast and flour. So you would go on to check, hey, do I have yeast and flour? Yes, I have, because I have yeast and flour. So bread can be made. Good. So bread can be made. Sandwich. When you look at sandwich, you see that, hey, sandwich requires this, and this is present in the list of supplies. But sandwich requires bread. Is bread present in supplies? No. So here is the most important thing. What is that most important thing? The ingredient list for a particular recipe might contain another recipe. So when you look at the ingredient list of sandwich, there is bread. And bread is actually another recipe in itself. So sandwich depends upon bread. So it basically means that if you can make bread, you can make sandwich also. And if you can't make bread, let's say bread required yeast and there was no yeast in the supplies, then you can't make sandwich also. So that sort of dependency is there. So one recipe can depend on another recipe. And then this is quite intuitive, because I can very clearly say that, hey, let's say there is a mushroom pizza, and that mushroom pizza is a recipe in itself, and it has a dependency on another recipe, which is just a wheat base. So if I can make wheat base, then I can make mushroom pizza also. But if I can't make that, I can't make this also. So that kind of dependency is there. So whenever you figure out such sort of dependency based relationship in a question, then most of the times it turns out to be a graph question. Like here, if I have to model this entire thing as a graph, I would go on and say that, hey, let's just go here. Let's open a new file. And here what I'm going to show you guys is, so as you can see, uh, our supplies are of yeast, flour, and meat. So these are like raw materials. So they are always available. There are infinite quantity of them. So yeast, flour, and meat. So let's call it yeast. Let's call it flour. Let's call it meat, right? And now I can see one thing, that there is something called as a bread, and bread is actually a recipe. So let me put recipe inside this box. So there is a bread, and if you look at the ingredient list of bread, bread requires yeast and flour to be there. It is flour, flour. So spelling mistake, never mind that. And if you look at sandwich, then that sandwich guy, it requires this thing, and it requires bread. Okay, right? So this question can easily be modeled as a graph question. Are you able to understand my point? Yes or no? Now, if you model this question as a graph question, what we have to look out for? We have to look out for that how many recipes can I cook? How many recipes are possible to be made? So how do you do that? What can be the way to do that? So all in all, I mean, to make this question much more generic by nature, I can say, what are the important things that you would look out for? So let's say there is a recipe A. Okay. Now recipe A has dependency on recipe B. Okay. And recipe B has dependency on some other recipe, let's say recipe C. Okay. And recipe C, it just requires uh, maybe it requires some water, and it requires some pepper. Yeah, let's say this is all that it requires. And these two things are available, so C can be made. Now if C can be made, B also can be made. Okay, and if B can be made, then A also can be made. So let's say A had a dependency on something else also. Let's say A had a dependency on another recipe, which was D. Let's call it D. And D just requires a lot of peppers to be made. Okay, this is just a normal edge. Okay, D just requires it to be made. And then yeah, so basically I can say that A can be made because I can make B also, and I can make D also. That's the idea. But you know, certain times it can happen that, let's say this D, it required pepper and it required sugar. Now if there is no sugar, then D cannot be made. And if D cannot be made, then it is guaranteed that A also cannot be made. So in this case, I can say only B and C can be made, because C required water and pepper, which is available, and B just required C, which is available, which can be made. A cannot be made, D cannot be made, because D required sugar and sugar is not available. So this is one case in which some or more recipes may not be made. What can be some other complicated case that comes to your mind? Like what can go wrong with this graph? Tell me. This is a dependency graph. There is dependency of cyclic. Very good. That's the most important point. There can be cycles. Let's say the ingredient list of C contains A, then that is a disaster. Why that is a disaster is because there is a deadlock. Recipe A would say that I cannot be made until unless C is made. And C would say, I cannot be made until unless A is made. So nothing would be made, as simple as that. Do you get the point? How many of you understand my point? Yes or no? So in this question, so do you see how this question translated to a beautiful question of cycle finding? And this is what happens. This is what happens in DSA. When you learn a concept, you have to be super strong at being able to apply it to different situations. No questions will tell you that find a cycle. I mean, your interview question will not be as easy as that. Your question would be something like this, where you have to identify that, hey, here cycle finding is important. And this entire data is modeled like a graph and all sorts of things. Correct? Okay. Once you understand this thing, then you can probably make an attempt to solve this question. Now, if you have to solve this question, have we already written a code to check whether a directed graph has a cycle or not? Do you remember the code that we just wrote to check whether directed graph has a cycle or not? Okay. Can we use the exact same approach here to find out that which recipes can be made and which recipes cannot be made? Can we do that? Yeah, everyone else? Do you want to give some 3 to 5 minutes of thought on this on your own? You just put in some thoughts, think of some pseudocode, think of what are the variables that you need to track and how do you want to go ahead with it. So just think about it for a while. Yeah. You can take out your pen and paper, write something, draw some graph, and then only you will get some clue. You should have some pseudocode at least in your mind. Okay, so one of you is saying on the way we have to set is possible flag of a child to true and a function that tells it's possible to make this recipe. Yeah, good, good, good. Yeah, that's a good point. See guys, let's say this is the graph. This is a simple graph that you have for now. And we know that all these recipes can be made. A, B, C, and D, all of them can be made. We know that. Okay. Now, the list which is given to you, that list can contain these recipes in any order, isn't it? It could contain C and then it could contain D and then it could contain B and then it could contain A. So what I'm trying to say is that you can have a list that just holds something like C, then D, sorry. Yeah, let's say then D, then B, then A. So in this case, you would first, make a function call for C. Probably let's say you're doing DFS and you see that, this node C, it requires water and water is already in the list of supplies. Very good. Pepper is also there in the list of supplies. Very good. So C can be made. Now you come to D. In case of D, you see that, hey, D only requires pepper and pepper is there in the list of supplies. So D also can be made. So basically you say that, hey, C can be made and D can be made. And you store this information somewhere that C and D can be made. Now you come to B and now you see that, hey, B requires C. C is not in the list of supplies. C is not in the list of supplies. C is a recipe in itself. But now, because you have already found out that C can be made, so you can say that, hey, B also can be made. Similarly, when you go to A, you see that A depends on B and D. Both of them are not supplies, they are recipes, and we know both of them can be made. So A also can be made, as simple as that. But this data can be given to you in any other form also. So let's say it kind of starts with B. So if it starts with B, and if you start looking at the ingredient list of B, the first thing you will find is C. And you will find it out that C is not in supplies list, but C is actually a recipe. Now, if C is a recipe, you would want to solve for C. And if you want to solve for C, you would want to make a recursive DFS call to C. So it involves jumping from one recipe to another recipe. And if you have found a solution for a particular recipe, whether it can be made or not, then you should store it. which is what one of you is calling as memoizing. So you want to store it somewhere, whether C can be made or not, whether B can be made or not, so that you can use that information to conclude the result of other recipes, A and whatever you have. So that's the basic idea. So what we will be doing is we will be I would say one thing, that all these supplies, they are anyways available, right? So what I can do is I can just have a list, and in that list, let's say that is a list which contains all sorts of possibilities. I mean, what are the items that I can make, that I can have, in general I can have. So I would say that, hey, I have infinite supply of yeast, flour, and meat. So I would initialize it with yeast, flour, and meat. This is how I would initialize it to this list or this set. It can be a simple set. And now what I can do is that I can start iterating on my recipes. The first recipe that I find is bread. Okay, so let's pick this bread guy. When you pick this bread, you would be curious to look at its ingredient list. And you see that in its ingredient list, you have yeast and flour. Okay, and now you find out that yeast is also present here in this set. Flour is also present. That means bread can be made. Because bread can be made, so I can put this bread here in this list, right? Okay, so bread is possible actually, right? Now we would move on to the next item in our recipes, which is sandwich. When I pick my sandwich and when I look at its list, I find out that, hey, this sandwich, it requires bread and meat, right? So let me just type it here. The first thing is bread. Now, is bread in the list of supplies? No. So I would want to just check. So I would basically want to check whether whatever this item is this item present in this particular list or not? If this item is present in this list, very good. It means it can be made. Again, this item, is it present? Yes, it is present. So all that I have to do is, for every recipe, I have to iterate on its ingredients. And for each ingredient, I just have to check whether it is present inside this is possible list or not. If it is present, very good. If it is not present, then there can be two things. The first thing can be that, hey, it was not possible to make that item. If so let's say your bread said that I need a yeast, I need a flour, and I also need some, let's say, lemon. Okay, had that been the case, you'd have seen that, hey, this bread cannot be made, and you'd not have inserted it here. Now, when you come to sandwich, you see that bread is not there in the is possible list. If bread is not there in the is possible list, it means two things. Either you have not visited the bread, or you have visited it and you found out that it could not be made. Like in this case, in this specific case, you had visited the bread. So you have to somewhere store this information also, whether a particular recipe was visited or not. If that recipe was visited, and if that is not included in this list, that simply means that that could not be made. Now, because that could not be made, so this also cannot be made. But on the other hand, if you see that this was visited and this is included in the list, then that means, yeah, you can go ahead with it. And in case if this was not visited at all, then you can trigger a DFS over here. You can trigger a function call over here. So this is the logic that you have to have. Now in this entire thing, the important thing is you have to track cycles also. So if at any point of time, you see that there is a cycle, let's say sandwich had a dependency on something called as Coke. And let's say then you had another thing called as Coke, whose ingredient list started with sandwich. Then here you are in trouble because sandwich says that, hey, I need a Coke. Now you see that Coke is not visited. So you trigger a DFS call on Coke. Now, when you trigger a DFS call on Coke, you see that, hey, Coke also required sandwich. And basically now they are in loop. So it's case of directed graph, and we can track this loop through that variable, which we make true at the end, at the start of recursion, and make false at the end of recursion, right? So this is one simple approach that you can have. When you go ahead and try to code it, you will find that it's little challenging to write the code, and because it involves you to be really good at recursive logic. If you don't have a good understanding, you might fall here and there. But is the basic logic clear? How many of you are clear with at least the basic logic of how you can frame an algorithm for this question? Everyone else, yes or no? Yeah, okay, great. So whatever I have discussed, I'll show you the code of that. And after the class is over, you guys should go back and try writing your own code. So you can see there is that set of is possible. Okay. And I have initialized it with everything in the supplies. So let's say inside supplies, we had yeast, flour, and corn. So I have initialized it with them. And now, you might question why I'm keeping this map. I'm keeping this map because if you look at it, you have something like recipes. So it's a list. So bread is at position 0, sandwich is at position 1. If I look into the ingredient list of sandwich and I see bread, then I would want to know whether this bread could be created or not. Or let's think of it in this manner. Let's say this sandwich came before. This sandwich came before, and you found out that in the sandwich ingredient there is bread. So now you would want to know where exactly this bread is present. So what I'm doing is I'm making my DFS call at a particular index. So so let's say this bread is at index 0, then I call DFS of 0. Now, if let's say bread has a dependency on something, let's say sandwich, and sandwich is at index j, then I want to recursively make DFS call at j. So that is the only thing for which I have created this map. Sandwich is dependent on bread, so can't we find topological sort of recipe and according to, but do you think just topological sort will be able to solve this question? Just topological sort. Do you think that? So just think about it. Okay. I did not talk in terms of topological sort because I did not talk about that in class right now. I just talked about a very simple cycle finding thing, and you can just use that to solve the question. Okay, so in this particular map, I have the recipe and the index of that recipe. So bread comma 0 and sandwich comma 1. That is what I'll have in this map. Now there is a Boolean flag. I have this flag because I need to track cycle. This flag will be turned to true whenever something is pushed in the call stack, and it will be turned to false whenever we are popping from the call stack or we are returning. Okay. Is visited, why is visited is there, you all know, because it's a graph, so a node can be visited again and again. Now you can see what we are doing here is I'm just iterating on all the recipes. So basically I'm iterating on this list. And then if I check that this particular recipe is not included in that list, then I would want to take a shot at it. I would want to determine whether it can be made or not. So I want to trigger a DFS call. Before triggering DFS call, I have made it is visited as true. And I have sent the other important data structures that are there. You understand what all these mean. Is possible, which tracks all the items that are possible. Recipe index, I already told you. Everything else, okay? Now let's come here. This is the most interesting part. This, you understand, the moment something is pushed on the stack, we convert its flag to true, okay? This for loop is just iterating on, the ingredients, okay? So ingredients I is the list of ingredients for recipe I, the ith recipe. So I'm iterating on it, and what I'm doing is this is ingredients ij, it is the jth member of that list. So if recipe index dot find this thing is not equals to recipe index dot end, so this line basically means that if that particular ingredient is inside the recipe map, that means that it's a recipe. That means it's a case of sandwich depending on bread. It's the case of one recipe depending on another recipe, right? So in that case, what I would want to do is I would want to get its index, that at what index it is located, and then I would want to look out for this thing. If flag of that index is true, that means there is cycle. Then it means that current depends on index. So sandwich depends on bread, and then bread also depends on sandwich. So if this is the case, then I just wish to return. I just wish to exit from here. Otherwise, I want to first check whether that index is already visited or not. If that index is not visited, so let's say sandwich depends on bread, bread is at this index, and if that index is not visited, then I want to do a DFS. Before doing DFS, I make this is visited as true, and then I trigger a DFS from that point. After that, once this thing is done, if the item at that index could be made, then it must have got included in the is possible set. So what I am doing is that if is possible set, if it contains this jth item, whatever that recipe is. So let's say sandwich depended on bread, and when you made a DFS call on bread, the bread must have got included. So if it got included, then what does it mean? If it got included, then that's well. But if it did not get included, that means sandwich depends on bread and bread cannot be made. So this condition, if you guys know a little bit about how to use set and all, this condition means that this item, ingredients ij, it is not present inside this set. So if it is not present inside this set, it simply means that that item could not be made. And if it could not be made, then you can turn the flag of I to false, and then you can just return from here without including that current item. So it means that current item also cannot be made. There is one else if condition also. This else if condition is for the case where, so you can see that this else if corresponds to this. So if your jth item in the ingredients list, if that was not a recipe, if that was not a recipe, then you simply want to check whether that is present in supplies list or not. Now, if it was present in the supplies list, it must also be present in is possible, because the first line we did was we mapped all the supplies to is possible set. So if it is not present, then again, I would want to set the flag as false and then return without including that item. Now think of it in this manner. If this loop successfully executed, then what does it mean? It means that all the dependencies of current or I, all the dependencies of I, they could be made. Either they were present in supplies, or they were a recipe that could be made. So in that case, what we are doing is we are inserting that recipe I inside is possible. So, what will happen is that eventually, once I have run this for loop, that list, once I have run this for loop, then this list is possible. It will actually contain all those recipes only which could be made. So finally, I am just iterating on all the recipes, and I am checking whether that is present inside that set or not. If it is present inside that set, then only I am including that in my answer. And then finally, I am returning that answer. Okay. So could you relate somewhat with the code? If not entirely, I mean, it's a long code, but could you relate the logic parts that I had given somewhat with it? Okay, completely, that's great. Okay, the next thing that you can do is, like, when you go back, you just think about that how this simple concept of cycle finding could be applied in a question like this, and how we could solve something like this quite easily. There are a lot many concepts actually. I plan on to take probably some other sessions also on graphs, where I can go on to talk about some other concepts, but just this concept is also, can give rise to some really, really amazing questions. Like some questions which can be solved using topological sort. They involve somewhere the idea of finding cycles, because if cycles are there, then there is a big problem with topological sorting. That just can't be done. So this cycle finding, it frames an important class of questions in case of graphs. How to tackle cycle case, that's been taken care of. That's what I told you. So you can see here this thing and this thing, right? Now, let's say let's say you found out that you have a dependency on index IDX. So you make a DFS call on that, right? But before making DFS call, what you first do is you check the flag of IDX. So think of it in this manner, that your current index I is sandwich and your IDX is bread. Okay. Now, let's say bread is already in the call stack. If bread is already in the call stack, that means flag of that bread would be true. So that means bread somehow depended on sandwich, and now sandwich is asking for bread. So that's problem. So in this case, we simply return and we do not include the sandwich inside the uh, list, inside the set. Yeah, we just return from there. Okay, cool. So now what you guys can do is, when you go back, you can also, there is this similar questions thing. You can just click on count good meals and just click on this. I'm not sure what question this is. This is the one. You can probably look at it, and it could be a different question also. I'm not really sure if it is dependent on the same concept, but I'm sure you will get to see a lot of questions which are dependent on this exact same concept, and you can try that out. A good question that you guys can try out, I wanted to discuss it today, but probably I'll take it for the next time, is this question. It's a good question. I'm just sending it in the chat box. So if you want, you guys can even try this out as well. Okay. And yeah, so I believe you guys understood at least this one part, the cycle finding part, and how it is different in case of directed and undirected graph, and how you can apply it into certain problems, right? So now the next thing that you can do is, whatever learning you have, feel free to summarize that learning anywhere, wherever you want. You can just do it on LinkedIn. I think I have Archie here with me. She'll probably share some sort of a link which will contain a post about this event that we have done. You can, yeah, she's sharing it in the chat box. So you guys can just go there. If you feel, you can comment whatever was the key learning for you. Okay. And you can also repost it, and you can share it with, you can share whatever your key learning was. So that will help us figure out who summarizes the event in the best possible way. But yeah, just before we end, anyone who would like to talk about the important things that we discussed yesterday, that we discussed today. So what were the key things for you? What were the key takeaways for you for the today's class? Anyone would like to start that? DFS and cycle detection, of course, yes, that was the most important thing. And can you just relate that? You might have heard that there are so many complicated algorithms in case of graphs, but let me tell you, a good interviewer, a good organization can give you a very good question which involves nothing else than DFS and BFS. So if you are just good with basic recursion, some sort of backtracking, DFS, BFS, you will be able to solve most of the questions. And trust me, what I say, I mean, you will be able to do that. Okay. So fundamentals play important role. Implementation of a basic thing like finding cycle can be structured to a question. Yes, yes, all these things. Okay, then great. So that will be it for today. Uh, Summarize your learning and win the goodies from our side. Okay, that's it. Bye everyone and good night.